Have you ever wondered why a pendulum swings the way it does, or why certain objects vibrate at a specific frequency? Today, we dive into the fascinating world of pendulums and vibrations, unraveling the physics that govern these simple yet intriguing phenomena. We'll start with a simple pendulum, which is essentially a weight suspended from a pivot so that it can swing freely. The task is to verify the relationship T equals 2 pi times the square root of length over gravity. This is done by measuring the time it takes for the pendulum to complete one full swing or period, and comparing it with the calculated value using the formula. The length of the pendulum and the acceleration due to gravity are the two variables that affect the pendulum's period. Next, we'll determine the radius of gyration of a given pendulum. This involves setting the pendulum into oscillation and timing a certain number of complete swings. Using the known mass and length of the pendulum, along with the measured period, the radius of gyration can be calculated. The third experiment is to verify the relation T equals 2 pi times the square root of OG over G. Here, OG is the distance from the pivot point to the center of gravity. This experiment involves similar steps to the first, but with the added variable of the center of gravity. Moving on, we'll determine the radius of gyration of a given bar using a biflyer suspension. This is done by suspending the bar from a pair of strings and setting it into oscillation, then measuring the period and comparing it to the calculated value. Output. Next, we delve into the realm of vibrations. Starting with the longitudinal vibration of a helical spring, we'll determine the frequency or time period of vibration, both theoretically and practically, by setting the spring into motion and timing its oscillations. We then study damped torsional oscillation, which involves twisting a pendulum and observing how it slows down due to damping forces. The damping coefficient, a measure of how quickly the pendulum comes to rest, is then determined. The following experiment involves finding the natural frequency of undamped free vibration of an equivalent spring mass system. This is done by setting the system into motion and measuring the frequency of its oscillations. Next, we'll study the forced vibration of a similar spring mass system. Here, an external force is applied and the resulting vibration is observed and analyzed. Then, we'll explore the torsional vibration of a single rotor shaft system, determining the natural frequency of vibration, both theoretically and experimentally. Finally, we'll study the free vibration of a two-rotor system and determine the natural frequency of vibration, both theoretically and experimentally. We'll also study the forced lateral vibrations of a beam for different damping. Through these experiments, we discover the intricate interplay between forces, motion, and energy that govern the physics of pendulums and vibrations. We learn that seemingly simple systems can exhibit complex behavior, and that understanding these systems requires a careful balance of theory and experimentation. So the next time you see a pendulum swing or feel an object vibrate, remember there's a world of physics waiting to be explored.